Thanks. I will try to walk through most of the details. Yeah, so hash-based signatures are one of the standardized schemes in the NIST competition. So we have the Sphinx plus signature scheme, which is now SLH-DSA for a stateless hash-based digital signature algorithm. And there were actually two proposals which are stateful, which means the secret key changes over time, in contrast to a standard signature scheme where just the secret key is a stateless object which you store, and you can store several copies all over the place, which you still shouldn't do for other reasons. But in stateful hash-based signatures, this is a problem because you would have to keep all these states in sync. And there were two proposals which were, I would say, are roughly the same scheme up to some details, which were specified as RFCs and taken up by NIST in the special publication on 800-208. And they were kind of the first post-quantum digital signature scheme that you can use in practice. And so this is what many companies use for firmware updates and started implementing nowadays. The whole thing, as most of post-quantum crypto, goes actually back to the beginning of the 80s, end of the 70s. Merkel also had some reviewer B issues, so this paper only appeared 10 years later. So for PhD students, if your paper doesn't get out, doesn't mean it's not impactful, it just means you have an asshole reviewer, potentially. I mean, you can still win some prizes with this. So why is this stuff interesting? Well, because it's inherently post-quantum, because Grover's algorithm doesn't hurt hash functions, and something like Shor doesn't work for cryptographic hash functions, except if you're intentionally building in number theoretic problems. And the key is you really just need a secure hash function and nothing else. You don't need an MQ problem, don't need a shortest vector problem or anything like this. For hash functions, the security is pretty well understood. So we had this SHA-3 competition after SHA-1 was attacked. And that gave a pretty significant boost, I think, to our understanding of what a secure hash function is and how to construct these things. And these schemes are actually pretty fast if you allow for state. The stateless schemes are okay, but they take their time. Well, and for some time they were really the first ones that were actually standardized. Okay, so in some sense you can say these have minimal security assumptions, because if you look at any scheme like dilithium or all the schemes that Monica just talked about, or RSA signatures, standard DSA, they all have some intractability assumption, right? There's either you have RSA, you have discrete log, or you have some bilinear group stuff, whatever. And then you have, in addition, a cryptographic hash function, which for most of these schemes you actually are modeling as a random oracle, because otherwise you don't get any relevant proof for any practical scheme. And for hash-based signatures, this side just goes away. So you really just have this assumption that you have a cryptographic hash function, and if you have one that behaves more or less like a random oracle, then you're actually fine. Then you get a signature scheme. If you have one that only has certain standard model properties, you still get a signature scheme, but it can be less efficient than you might want it to be, if you really want to get entirely away from random oracle assumptions. Okay, so let's briefly recap stuff that you probably have seen in Crypto 101. So in general, when I talk about hash functions, I think of hash function families. There are two reasons, not information theoretically. If you look at the complexity, from a complexity theory point of view, something like collision resistance doesn't make sense if you don't have a family of functions, because otherwise I can give you an adversary that always just outputs a collision for the one function, right? And this does this in constant time. From a more practical point of view, we actually need to domain separate these hash functions. If you don't do this, then you can attack a lot of stuff at the same time with queries, so the complexity of attacks actually goes down. We want these functions to be compressing or at least length preserving on a message input. So if we ignore the key, then this is essentially an n-to-n bit function, or m to n where n is larger. Yeah, and we want it to be efficient to evaluate. And one remark here, in general, this key is actually public, right? This is a salt or a function description, like an initialization vector, so something that everybody knows, or that is part of, for example, a public key, but is not kept secret, with one exception that I will come to in a minute. So one way is just ask an adversary to actually come up with a pre-image of a point y, where y is actually not just sampled from the codomain, but from the image space, right? So we're sampling a random input, evaluate the hash function on it, and then give the hash function description, so the key k, and this image to the adversary, and they have to come up with some x which reproduces y, and this x prime doesn't have to be the original x. We don't care about that. And then collision resistance, you should know, is if I have two different inputs which produce the same output under a hash function, they form a collision. That is problematic, for example, if you have a signature which signs a hash value. If I can find such a collision, then I suddenly have essentially a signature for two values, right? But actually in practice, what usually happens for these signatures is I get a signature on a message, and then I would have to find a second signature or a second message for which the signature holds. And then I'm looking at second pre-image resistance. So in this case, half of the collision is actually given externally. And I have to come up with the second half of the collision. And there is a decisional version. I think I will not come to a discussion where this becomes relevant. But you can think about the question, if I give an adversary an x, does there exist a second pre-image for this x? And then we have one non-standard property that we need for hash-based signatures, and that's called undetectability. And this essentially means, can I recognize if something is the output of a hash function, or just a random element from the codomain? So in this case, really the full codomain. So we're playing a game, or the adversary plays a game, where they either get the image of a random point, or just get a random codomain element. Right? And for example, you can distinguish this if the image is extremely small within the codomain, and then you know where the image lies. So whenever this thing lies outside, you can actually detect this. But if you look at random functions, then usually the image is comparatively large. And so this is something you can hardly actually decide. And then the last property that we need is pseudo-randomness. So this is the exception where the secret key, or where the key actually becomes secret. So that says if I actually sample a random key and keep the secret, then if I just give you access to this function that's produced, you cannot distinguish this from access to an entirely random function. All right, so if we model this as a game, then the adversary gets access to some black box, which is either instantiated by sampling a random key and then putting the corresponding hash function in, or just sampling a random function from the set of all functions, putting this in. Yeah. And with this, you can, for example, build the length doubling PRG as you need for these PRG trees that Monica just mentioned, because you just run this thing in counter mode and you get two outputs. And if the key and the output space are the same, then this gives you a length doubling pure G. Okay, so I will not go into hash function cryptanalysis because this is entirely beyond my expertise and also not what I'm too interested in. What I rely on is that in general, hash functions are considered insecure when they don't meet what's called generic security, which is kind of the optimal security that you can reach, which means there are essentially no non-black box attacks. Right? So black box attacks are essentially everything you can do without looking at the internals of a hash function. So if I just say, this is my black box hash function, if this thing is compressing, I can always find collisions. Right? They always exist. They have to exist by the pigeonhole principle. So if I just query long enough, I will eventually find one. But that doesn't mean that it's not hard. And so this generic security for hash functions is well, the hardest case is if you actually have a random function family. And the complexity is often expressed in the number of queries, or query complexity. So let's look at this briefly. Classically, we estimate this by just looking at the statistical game. So if you just do a single guess for breaking one winners without looking at the hash function at all, you have a 1 over 2 to the n probability of actually hitting this, right? Because your output space is 2 to the n. So that you guess the right one is 1 over 2 to the n. With every query, you get one chance to actually check if you hit. And there are two cases where this happens. This definitely happens whenever you have, so this is not really an equal, but there would be a 1 minus this here as product. But either I might have hit exactly the x which was used to produce the output, or I might have just hit some input which actually hit the output. And so in the end, I end up with something around 2q over 2 to the n if n and m are the same. And if m is much larger, then this thing entirely vanishes and we don't have to care. Does it make sense for everyone? Okay. So in most analysis, this part is actually not there. You see, I also added it later because we usually think about massively compressing hash functions, and then this term is just, you don't care. But actually, for hash-based signatures, we often think about length-preserving hash functions, and then this term actually matters a tiny bit. M is the input length. Yeah. And so if m equals n, then you actually end up with 2q instead of q. Asymptotically, in any case, this doesn't matter because you always end up with 2 to the n, but if you're counting bits, then that actually makes 1 bit difference. If we come to the quantum case, the whole business gets a bit more complicated. Essentially, well, we do have methods to directly estimate this, but this is kind of a pain. What we do instead is we have some quantum hard problems that we know. For example, distinguishing a constant zero function from a function which has a 1 in a single position, if I'm always just allowed to query single positions of the function. Then we do have bounds for this coming from the optimality of Grover. And then you can actually give a reduction of this problem to the hardness of, for example, finding pre-images. And then you come up with the query bound of 2 to the n over 2. And this is also matched by Grover as the best known attack. And you can do this for all these properties. And then you get this table essentially everywhere. You get 2 to the n, 2 to the n over 2. Except for collision resistance, there you have 2 to the n over 2 already classically, and that increases to 2 to the n over 3 quantumly. You can have a long debate if this is actually meaningful, because this needs 2 to the n over 3 quantum storage, which you can debate if this is feasible, but so be it. Because this thing you can do essentially with storage, with constant storage, right? You can do pollard row and then you don't need any storage for that. Okay, that far with preconditions. Any questions about this? Okay. I think it's 76, Lampert, in some unpublished report, I think for the military, came up with this beautiful idea of, hey, you can actually use this to build signature schemes. So if you want to be able to sign a single bit, you can pick 2 random bit strings, which become your secret key. You take the hash values as public key, and if I want to sign bit 0, I publish the secret key. If I want to sign bit 1, I publish the secret key as my signature. Obviously, I can only do this once because I already leaked half my secret key, so everyone can sign the bit again. And actually, as soon as I sign 2 different bits, like all my secrets are gone. You can expand this to longer bit strings, and the idea is pretty simple. I just sample a lot of these pairs, right? 1 per bit, and then you do the same game bitwise. So like from every pair of secret keys, I just pick one of the secret key elements depending on my bit, which usually will be the bits of a message hash, and that gives me the signature. And the same argument holds up to some details, like if I'm signing 2 messages, actually if I have full control over the messages to be signed as an adversary, then I can just ask for 2 complementary messages, right? All 0 and all 1 string, for example. I have the whole secret key state, the whole thing is done. If these are actually randomized message hashes, then it's not as terrible, but the effort to actually at least come up with a universal forgery suddenly becomes pretty low. Does everyone know what's, okay, so signatures in general, security is defined as a setting where an adversary can observe signatures under a secret key, has the matching public key, and in the end has to come up with a forgery where the message was not used before, right? And a one-time signature is just a signature scheme where the adversary has exactly 1 query that they can make here. Because again, if they can make 2 queries, then they can learn the full secret key. And for Lampert's scheme, you can actually show that the scheme is existentially unforgeable under chosen message attacks if the hash function is one-way. And I will not bore you with how it works, but essentially you have to place a one-way challenge in one of the public key elements and then just hope that that the adversary picks this one to change the message. Okay, now one-time signatures are beautiful, but they are not very helpful, right? I just, instead of bringing the message in a trustworthy way, in an authentic way to the recipient, I have to bring the public key. I didn't gain that much. Maybe besides delay, like I can actually exchange the public key at a point in time when we meet and can actually send the message at a later point in time. So Merkle came up with the idea that we can actually build a many-time signature scheme by just using a lot of one-time key pairs and authenticating them all by a single value. And for this, he used what's called a Merkle tree. So Merkle tree is a binary hash tree where the leaves in this case are just the hash values of the one-time public keys. And then any internal node is the hash of the concatenation of its 2 child nodes. Right, so it's, in this case, if you remember the seed tree, that goes top down, this one goes bottom up. You can go up, you cannot go down. So the root node now becomes the new public key. This is the thing that you actually hand out to your communication partner. all the one-time secret keys become your secret key, you can compress this thing just by a PRG, right? These are random values, so you can generate them using a PRG. If you use a PRG with counter, then you can just generate them on demand without having to generate all the previous keys first. And now, one thing to observe is these are all one-time signature schemes. So I somehow have to make sure that I'm not using any of these secret keys more than once. And so the easiest way is just saying like, okay, I used them from left to right. I remember where in the tree I was. The ones before I'm not using anymore. The ones after are the ones that I'm using. This also has some advantage because if I assign a message, what I do is I pick the current one-time signature scheme. And then I sign a message using the corresponding secret key. So this gives me a one-time signature. And I have to put this one-time signature and the one-time public key into the signature. But in addition now, somehow the verifier has to be able to link this one-time public key to the root node. And so I have to include what's called the authentication path. Right? And the authentication path are the sibling nodes on the way up. This should become red anyway. On the way up from the one-time public key to the root. And if I'm traversing this tree from left to right in order, then actually every second time this path only changes in a single node. So if I store the last path, I actually can speed this up. And there are algorithms to compute these nodes efficiently. And it is relatively straightforward to prove that if the one-time signature scheme is secure and your hash function is collision resistant, then this thing gives you a secure many times signature scheme. Right? The idea is either someone has to produce a forgery or must have included a one-time key pair for which they know the secret key into your tree. And if you actually put a new leaf in here, then there will be a collision with the original tree path. The slides will be, actually, I don't know how many versions of this are online on my website. So. Okay. If you look at these signatures, the largest chunk is actually this part, by far. Like the authentication path is comparatively small. But here, if you think about Lampert, it was 2 times the number of message bits, right? So if this is a hash like 256 bits, times the length of the message hashes that you need in here. So this is quite a chunk, while these are single hash values. And there are actually better versions than this. So if we optimize that part, we actually gain a lot. And so if you look at how verification works, then what happens is we first verify the one-time signature using the one-time public key, and then we verify the authenticity of this one-time public key. These are kind of separate processes. And we can actually do better than this. So there's a first trivial optimization where I just include the public key component in the signature where I don't output the secret key, right? So from every pair, I pick one secret key element and then the public key element of the other half of the pair. This means I always can recompute the public key from my signature. I just have to hash the component which is indicated by my message bit, and that should give me the full public key. Why would I do this? I mean, actually, this increased the signature size, right? It doubled it effectively. But if I look at my scheme, how I use it, this actually is an advantage because I can get rid of the one-time public key in this whole thing. So now my process changes to, I don't verify the one-time signature using the public key, but I compute a candidate one-time public key from my signature. And then I verify the authenticity of this value. And that should not work if I computed the wrong one-time public key. So together, this gives me the verification also of the one-time signature. Yeah? We can even do better than this. So if you sort these things, then you see that in some sense we have encoded M and its inverse, or its complement. And the signature contains the secret key if the bit was 1 and the hash of the secret key otherwise. And we included the complement to make sure that whenever one bit flips from 1 to 0, another bit flips from 0 to 1. All right? Because that means the adversary has to break one-wayness of the hash function. But this is actually far too much. Like, this is kind of a checksum with bad performance, and you can actually do better than this. So there's an optimized version, which I think goes back to Diffie, if I'm not mistaken. And this is actually all of Merkel's original paper. So the proposal is, instead of putting the complement there, you sum up all the bits of the message and then take the complement of the sum. Right? So let's see what happens. If I switch some bi from 1 to 0, then the sum actually decreases, which means there will be at least one, there will be at least one which flips to 0, which in consequence means that in the complement of the sum, there will be at least 1 0 which flips to 1. And the good thing is, I suddenly reduced my signature size from 2m to m plus 1 plus log m. And log m is, I mean, this is essentially m, right? So, more or less. Is that clear? Okay. But so the Winternet scheme actually goes even further, and the idea there was that you can actually even add function chains. A function chain is something where I just evaluate a hash function multiple times on the same input, right? I evaluate it once, I evaluate it on the output of the first iteration, and so on. And I can see this as a chain if I look at the intermediate results. Right? So I have x, I have h of x, I have h of x, I have h of, and so on. And the nice property is I can easily go this way, but going this way is hard. Proving that going this way is hard is also hard, but it's a different story. And so here we're actually doing kind of the same thing as before, but now instead of having a bunch of secret key elements and just their hash, we have a bunch of secret key elements, hash chains on them, and then the public keys are the ends of these chains. I would have put them like 90 degrees turned, but then they wouldn't fit on the slide nicely, so sorry for that. And this L is essentially the message length divided by the logarithm of this of the length of this chain. Okay, so how do I sign with this? I take my message, and now these chains are of length w for parameter w. What I do with my message is I represent it as base w numbers. So in practice, we mostly fix w to be 16, right? So we actually chunk this into 4-bit blocks. Interpret these as numbers, then we compute a checksum, which is more or less the same thing that we had before, but moving from bits to integers. We represent this checksum again as base w numbers, so we split it into 4-bit blocks. And then we map this whole thing to our hash chains. So the first number tells us the how manyth node we take from the first chain, and so on, until the last number actually tells us the how manyth element we take from the last chain. And so our signature becomes the set of intermediate values of these hash chains. Right? And for verification, this stuff is public information, right? Like if I have the message, I actually can recompute this message mapping. And so I know which nodes within the chains these signature elements should be. And then I can just complete the chains. Right? So I continue the hash chain until I end up at the final node of the hash chain. And then I check if these actually match the public key, or if I'm in a Merkle signature scheme, I actually continue with these values as public key and see if this one is actually matching my authentication, or if they produce the same root node. So the original scheme simply used plain hashing. Then we had a proposal where we used the PRF. That turns out to be maybe not use it because we don't know how to prove it, because the proof was definitely flawed. And then what is currently used quite a lot is what's used in XMSS, which you call what's plus. So there, in every iteration, we XOR a random element. And the reason for this is that this allows you to go from a proof that requires collision resistance to a proof that requires only second preimage resistance. Why I would do this, I will explain in a second. Right, so for security, what you get is if you have this just iterating the hash function, the scheme is secure if the hash function family is collision resistant, undetectable, and one way. And for what's plus, you replace collision resistance with second preimage resistance. But you still need undetectability and one-wayness. So what happens for performance? If you look at optimized Lampert for 256-bit messages in W equals 16, you have a signature size of 265 message digests, and you need to do about 132 hash function calls. For winternits, we gain about a factor 4, yes, a bit more than a factor 4 for the signature size at the cost of about a factor 4 in signing time. One thing I should note, because I've seen this in many papers, so I don't talk about public key compression because this is kind of what we do in the tree scheme, like I just moved this there. Obviously, if you want to use this as a standalone scheme, you can replace these ends of the chains with a single hash value, right? This is, you shouldn't use as public key like all the chain ends. Okay. So for XMSS, we looked essentially at these numbers. And if you look here, then you see that if you rely on collision resistance, you actually need twice the digest length to get the same security level, right? Compared to the other properties. And as our signatures are essentially a collection, like a bunch of hash values, this is directly a factor of 2 in your size. And if you did the calculation in the last slides, these signatures are not super small. Like they are okay, but like nowhere near elliptic curves. There's a second thing. If you look from a complexity theoretic point of view, collision resistance actually plays in an entirely different league. So we can show that you cannot build collision resistant hash functions from one-way functions, but all the stuff down here you can actually build from any one-way function. They are constructions. They are not efficient, but you know, at least complexity theoretic, they somehow play on the same level. And this is also reflected in practice. So if you remember, in 2004, MD5 was suddenly broken, and I'm not sure that they really just did this in 2004, but this is when we got to know about it. And a year later, they published the attack against SHA-1. And then in 2008, we had practical collision attacks. In 2017, we had practical collision attacks against SHA-1. But until now, people don't have the slightest clue how to do second pre-image attacks or anything of this kind for SHA-2 or even MD5. So you can make a bold statement, which we did in the Sphinx paper, and say like, hey, actually, if you can avoid collision resistance, you're even still fine with MD5. I would still not do it, but currently, we don't have any indication that things would go wrong. Right? While collision resistance is clearly broken, like we have demonstrated collision attacks. And so for XMSS, we had to go to actually get rid of collision resistance, so achieve collision resilience, among others, simply because this halves our signature size. So this needs, and I cannot explain why in detail, but that in the tree you add bit masks, also like randomization elements, which allow you in the security proof to play second pre-image challenges there. For the leaves, like the hash of the Winternet's public keys, you actually have to use a tree instead of just hashing them, because then you can do the same trick as above. For the one-time signature scheme, we use a Winternet's plus, and for the message digest, we use randomized hashing. So this one is a bit borderline because you can only prove this if you want to have this in any way efficient in the random oracle model. But at least you can definitely avoid collision resistance here. And then we actually added something that was already there for quite some time. One problem with these tree-based signature schemes is that the height of your tree actually determines the number of signatures you can do. Right? If I have a tree of height h, I can do 2 to the h signatures. So if I have a tree of height 20, I can do 1,000,000 signatures, more or less. The problem is, during key generation, I have to build this whole tree because I have to compute the root node. Now, 2 to the 20 is still doable, but if we are talking about something like 2 to the 40, this is no fun anymore. Like already on a constrained device, 2 to the 20 is actually too much usually. This will take too long. And so the idea is that you can actually slice your tree into different layers. Now, this does not just work by slicing, because to compute this node, I of course usually would need its 2 child nodes. So we're decoupling these slices by actually not linking them via hashing, but via a one-time signature. Right? So you can think about this as kind of a small certification authority or PKI. So we have a bunch of key pairs. The top one most signs the root nodes of the next one, and so on. And then on the bottom layer, you're actually signing the signatures, the messages. And so during key generation, instead of doing like 2 to the 40 hashes, or one-time signature, especially one-time key generation is actually the costly thing here, I can actually go down to something like, for example, 4 times 2 to the 10. Right, which is then just 2 to the 12 computations, which is significantly less. This even allows me to reduce my worst case signing times by a bit. Of course, this doesn't come entirely for free. The problem is, for each layer, we have to add one-time signature, and so these blow up our signature size. So you want to be very careful with this, but if you cannot actually do a single tree at once within your device, it might be worth the consideration to introduce one layer and link them by one-time signatures and take the cost of this increased signature size. Okay, one thing, I think I should have enough time, that pops up when you're using XMSS. So I said we're removing collision resistance. What you actually notice then is that you only use targeted security properties, right? So I give you something like one-wayness or second pre-image resistance. And it turns out that if you're using a high tree, like something like, let's say, a total tree out of 60, right? Then you actually end up with something like 2 to the 60 images of the hash function, and you can break the signature scheme if you can invert one of them. And this is something that significantly reduces your attack complexity, right? Because if you just think about it, if I'm just brute force hashing, every time I'm hashing, I suddenly have a success probability of 2 to the, let's say, 256 minus 66. So if I'm going a bit more to the borders and would use something like 128-bit hashes, this would entirely kill my security, right? Because I would have only something like 60 bits of security left. And you lose this also quantum, but it's not as bad. So this, because the square root actually also hits the improvement. You can think about this like you plug a bunch of dartboards on the wall, and if I just throw an arrow into a big chunk of dartboards, I will hit one of them, right? So what we decided to do is we essentially take the dartboards and split them all over the place, that I essentially always have to target a specific one, right? So in general, what we use for this is domain separation. And so the idea here was to add some hash address, which is unique within a key pair. So if you think about this whole structure of trees, then you can essentially number every hash that you do in the scheme. And you include this into your hash computation. And in addition, you take a key, which is used for all the hash function calls within a key pair, but is unique among key pairs. All right, so this gives you multi-user security. And when we were working on Sphinx Plus, we actually started to abstract this away and introduce the concept of a tweakable hash function. And that does exactly this. So we have public parameters, which is the function key. So that's one per key pair. We have a tweak, which is kind of the hash address. And then you have the message and the message digest. And so actually by now, if you look at papers on hash-based signatures, often we don't talk about security of keyed hash function families anymore, but about the security of tweakable hash functions, which are essentially hash functions with domain separation built in. Okay. So if you then heard all this, go to the internet draft or now RFC, you will actually see this thing does not exactly do what I described. It does a bit more. So it doesn't do plain XMSS, but it adds this multi-target protection. Something that I swiped under the rug is that all these randomization elements, you of course somehow have to communicate to your communication partner, because otherwise they cannot do the hashing. You can either include them in your public key and you can repeat them to some degree, but then you cannot get multi-target attack resistance. So in that case, you actually need different ones for every hash function call. And that is only practical if you pseudo-randomly generate them. Now, pseudo-randomly generating them is something that you would anyway do, right? If you locally do this, you would use sample or short seed and would expand this using a PRG. And then you would give all the outputs of this PRG to someone else. The funny thing is, in a security proof, if I now give the seed actually to the other party instead of the output, my whole security argument breaks down, because I cannot do this proof hop where I replace the output of the PRG by a random bit string. Right? This only works if I actually have a random oracle where I can just program the seed in. And so this is an assumption that you need here if you actually want to make this, to make a short public key. And then for XMSS, we instantiate these function families using SHA-2 and Shake. And essentially, this is a scheme that we described in 2016, not the original XMSS proposal, but something we called XMSS-T. And then there is the second stateful scheme, which is LMS. And they essentially say, like, OK, you anyway need random oracles, so let's do everything in the random oracle model. It's kind of a lie because this is actually, the thing was proposed in the 90s, I think, but no one saw it because it was just a patent. They never wrote a paper. So a little lesson, if you want your research to be known, maybe write a paper, not a patent. Jintai Ding can sing a song of this, and he earned it. Yeah. So what they do is, instead of doing a complicated thing which allows you to prove standard model properties, they essentially take the same inputs and just throw them into the hash function, compress it, and say like, we'll be fine. You still get domain separation the same way. And then essentially the arguments are the same. So I will not go through them. You can discuss, I mean, in XMSS, we essentially show you where things could go wrong, how exactly, also relying a bit more on the internals of the hash function. But if you look at the random oracle model, this all goes away. And actually for Sphinx, we had, in the end, this and this as two different versions. So this one we called robust, this one we called simple. The final standard only has this one. So this one we threw away, and this was a request by NIST, and I thought a bit about this, but essentially I see this as, okay, here we learned what could go wrong, and we see that this stuff doesn't really go wrong here, so we're fine with the less complex stuff. And the reason is also that this thing is 3 times faster, because you don't have to do this complicated computation here. Yeah, and this is all about actually how to instantiate these tweakable hash functions. That's the only difference. Like otherwise, the schemes are really identical. From this high-level view, this is exactly the same. Okay, something, some small discourse. Something we recently did was actually machine checking the security proof of XMSS and also Sphinx, because it turned out that there was an issue in some proof attempts that we made to further push the tightness of the security proof, which we then actually fixed in 2022. But what we now did is we actually used the tool called EasyCrypt, which is not easy at all, but gives you actually the chance to convince a computer that your proof is correct. And so we have a specification of XMSS in EasyCrypt, and we gave a security proof which really shows that if your tweakable hash functions have these properties, then your scheme actually has these security guarantees. And we recently did the full thing also for Sphinx Plus, because this was just kind of the XMSS part within Sphinx that we analyzed. Okay, maybe we do 5 minutes short break, and then, okay, let's continue. So, up to now, all the schemes that I showed you are actually stateful, right? So we had to make sure that actually the one-time keys are used in order. And this in general works great for settings where you have good control of your keys. So firmware updates, I said, is one example. I think that actually root CAs would be perfect for this, because you can derive forward security from if you implement this with the right PRG. Something like that, if I leak the secret key at some point, this doesn't invalidate any of the previous signatures. But there are settings where this is really an issue. So if people are backing up their secret keys, which I think is unnecessary for signatures, but comes from a time where you actually had to pay quite some money for certificates. Or if you're using multi-threading, so you have a bunch of servers using the same key. Again, in general, not necessary. Or you have a bunch of devices actually using the same key. Again, not necessary, I think. But in practice, we do this, right? We use the same key all over the place, which is really stupid, because if it gets leaked somewhere and the chances increase, the more I use it in different places, then you actually have to revoke everything instead of just the one key that was leaked. Then actually state is a disaster, like because you would have to keep this synchronized, and especially something like multi-threading is close to impossible. And then you have stuff like virtualization, right? So you have this load balancing applications which just will spin up a new machine from some state that if the load gets too high, if you have some copy of your key on there, which they use to actually sign TLS traffic or so, then you're doomed. So this is the reason why we actually looked into how we can eliminate the state. And let's briefly recap. So what we had first was we went from a one-time signature scheme using a Merkle tree to a Merkle tree signature scheme, right? This thing increases the number of signatures that you can do, but you pay actually in secret key size, you pay in key generation time, you pay a little bit in signing time, verification, and signature size. Then you can actually shrink the secret key again by using a PRG. That's what I mentioned. So this slightly increases the time at key generation and sign because I always have to call the PRG, but it massively decreases the secret key size, right? I can get away with 256 bits. And then we had this hypertree construction where we take many Merkle tree signature schemes and build a tree of trees, essentially, right? And so if I increase D, then my signature size increases and verification time increases, but signing time goes down a bit and key generation time goes down massively. Right? And you can actually drive this very far. So I can actually make D equals H, which means I have a one-time signature scheme on every layer, and I sign 2 one-time public keys with this, which means I now have not a binary hash tree, but a binary certification tree or a binary tree of one-time signatures. And this is actually something that Goldreich proposed. So Goldreich said, okay, build essentially a huge multi-time signature scheme, and then just randomly pick the index. Right? I always just, for every signature, I just pick a random one-time key pair. And if my tree is just large enough, they will never collide, so I'm actually fine. And I can actually optimize this by adding a by using really a hypertree structure where I build this in different layers. This gives me different trade-offs. But in the end, I still need, if I want a Q times signature scheme, I need a many times signature scheme which has 2 to the lambda times Q squared leaf nodes. So that after Q signatures, I still have enough security left, and the probability of collision is not too high. And so if I look at the impact compared to stateful, the signatures are enormous, right? Because I have a shitload of one-time signatures. Verification time is pretty costly because I have to verify a lot of one-time signatures. Signing time is actually somewhat okay. Key generation time is super fast. And secret key and public keys can also be small. And so in Sphinx, we actually propose to drive this a bit further. Actually, let's go here. So, okay. We de-randomize the index selection. This is just so that we don't have to deal with bad system randomness. But the key idea actually was, which I think is due to Dara Hopewood, to use something called a few times signature scheme at the bottom layer instead of a one-time signature scheme. And this means you can actually use the same leaf node multiple times. So in our case, it's something like you can use it up to 8 times, and afterwards security decreases slightly, right? And we actually use a hypertree for this huge many-time signature scheme. So we use different layers so that generating this whole beast is actually not too expensive and doesn't need too many one-time signatures. And if you balance these out, you actually get somewhat reasonable signature sizes. So you slightly increase the signing time and the key generation time by putting in the hypertree, but you massively decrease signature size and verification time. Yeah, and the main thing is that actually this multi-time signature tree you can make significantly smaller. So we're talking about like a tree of height 60 instead of a tree of height 256 and more, right? And actually one thing I should add, the height of this tree massively depends also on the number of signatures you want to do with this scheme, right? So in the original Sphinx paper, we said, yeah, something like 2 to the 50 signatures seems to be by far enough for this kind of signature scheme. Because Sphinx is also a bit slower, you actually, in this case, it works in our benefit. You will not do like 2 to the 80 signatures or so. NIST thinks 64 as a power of 2 must be great. This is what we also used for hash function input length. So you have to deal with 2 to the 64 signatures. For most signature schemes, the impact is rather limited. This impacts something like the salt size. For us, this really increases the signature size massively. So currently, there's a discussion on the NIST mailing list about actually dealing with something like 2 to the 20 signatures per key pair. And the beautiful thing is, because as I said, security doesn't immediately drop when you go beyond 8 signatures per few times signature scheme, but it starts to slightly decrease. You have something that you can select parameters such that up to 2 to the 20 signatures, you're perfectly fine. Up to 2 to the 30 signatures, you're still within, I think, 10 bits of the original security bound. Right? So if you're overshooting, you're not immediately insecure, you're just stretching it. Yeah, so this is just summarizing this. Okay, so the key new component here is actually this few times signature scheme. And this is something that follows, again, the original idea of this Lampert-Diffie scheme. And it's called HORSE, and it's due to Raisin and Raisin, I think. And they use, okay, maybe let's do it like this. They generate a long array, again, of random bit strings as secret keys, T, where T is a power of 2. And if you want to be able to sign m-bit messages, you need T, like log T, to be such that log T times K equals M. And well, K is, is the number of hash values that you publish later in your signature. Then you publish as public key, just as before, the hash values of these secret key elements. And now for a signature, again, you're publishing, as I said, K of these secret key values. And for this, what you're doing is you're hashing your message, and then you chunk your message hash into A-bit blocks, which will give you K if you follow these parameter alignments. You interpret these as integers, and you pick the corresponding value from the secret key. All right? So I have this here. Yes, you essentially then select the respective values from your secret key array and you publish them. So why is this secure? What you actually need is something called R-subset resilience. So essentially, our messages are mapped to k-element index sets, right? And so each signature publishes k out of the T secrets, or up to k out of the T secrets, because they can actually collide in this setup. And so, I mean, obviously, if you want to sign a message, you can break the one-winners, right? If you have the public key and you can break one-winners, then you can just compute all the secret key elements and you can forge. If you cannot do this, then the game actually becomes the following. After R signatures, you have seen the secret values corresponding to R different messages, right? And so now it must be still hard to find an R+1 message such that the indices that you need to actually sign this R+1 message are contained in the union of all these previous index sets that you have seen. Right? So there are actually information theoretic constructions which give you exactly this property. But they are called cover-free sets, R-cover-free set, R-cover-free families, I think. You can construct them. This stuff is horribly inefficient. So yeah, you could do it, but then the Sphinx would not be practical in any way. So what we do is we say like, okay, if actually our hash function is a random function, then this actually, if we just compute the indices as chunking up the hash value, this statistically actually gives us this property more or less, right? So in the worst case, we're actually getting R times k values. And so those are chosen out of T. I'm just thinking about why we have the k in the exponent. So with every query, okay, I don't get the equation together, I'm sorry. But this is in the end the equation that you get for the term of the probability that per query you're actually hitting such a cover, right? And you're doing Q queries, and you see that R appears in here. And so if I'm increasing R, this term actually increases. It's the k positions that I have to hit, yes. So I have to cover k positions, and each of them I have seen with probability R times k over T, yes. And so security shrinks really with every signature, but because really just this value increases, it doesn't shrink immediately to 0, but just slowly. Any questions about this? All clear? Good. Yeah, and then what we did is actually these public keys are enormous. So what we did is, well, we like trees, so we drop trees on it, and then you get something that we called horsed, which is horse with trees. And the idea is you just put a Merkle tree on top of this horse public key. And so instead of having to publish this whole set of T public key values, you actually have to publish authentication paths for each of the secret key elements that you're publishing. And then if you look at these paths start to merge at some point, and then you can either, there was a proposal which said, okay, if we just try a few times, you can actually make sure that they merge a lot, and then thereby we can save a lot in signature size if we don't publish nodes twice that you need. What we did is you can actually publish an intermediate layer of the tree and only do authentication paths up to this layer. And then the top part, the verifier then has to compute. So the verifier checks that your authentication paths actually arrive at this intermediate layer, and then has to compute the hash tree for the top part. And that gives you actually in the end the same time complexity. And so, for example, for the parameters in Sphinx 256, this dropped the public key size from 2 megabytes to 16 kilobytes. And this is actually more or less the largest chunk in the signature. Yeah, and in addition, so the original proposal used just a hash function, which means this gives you, so this property here gives you some form of a collision resistance property, just with a wider definition of the term collision. And what we did is we essentially moved it to randomized hashing, so you get some form of target or extended target collision resistance, I think it's called. Right, so this means the adversary suddenly cannot control anymore for which leaf, for example, or for which hash value a signature actually is. Okay, so in our first proposal, we actually gave one specific instantiation to reach 128 bits of post-quantum security. So you can do, we were a bit imprecise, by intent, hundreds of signatures per second. I think we, like at that point, the software took something like 200 milliseconds per signature, but is nicely parallelizable. Mark Hussarin had a nice proposal how you can actually massively decrease this by hardware acceleration, because if you can accelerate these hash chains so that you don't every time have to go out of the context of the hash function, you actually can gain a lot. And so this initial proposal had 41 kilobyte signatures and 1 kilobyte keys. So here we did not yet compress the these randomization elements. For Sphinx Plus, this goes down to 512 bits, and here it largely depends on which security strength you need. But for the highest level of security, so this is NIST level 5, you're still in that ballpark. Yeah, so for Sphinx Plus, the main things we actually changed is we strengthened security to get smaller signatures. So what I said before is for horse, these indices can collide, right? And if I find a target message that I want to sign which actually has a lot of indices colliding, that makes my task a lot easier. And so what we did is instead of having one large tree from which we pick all the indices, we split this into many little trees, and you pick one index per tree, which means if the same index appears twice within the message hash, it doesn't matter because it's from two different trees, and so they do not collide. It's not the same value. Right? And this actually boosts security and allows us to reduce the signature size. We added the multi-target attack resilience, which was not yet there in Sphinx because we only found this later. Yeah, I think the rest is, this was an advertisement slide from the first NIST conference. And now the internet might, yes. I was actually faster than I thought. Okay, so to conclude, yes, we do not need new assumptions to actually build signature schemes. We can actually just do from hash function security. If you can live with a state, then XMSS and LMS actually give you quite efficient signature schemes. If you need statelessness, then you will actually have to deal with SLH DSA, which comes with some penalty in size and speed. But as I said, if we finally get these small number of signature parameters, then these are actually not that large and slow anymore. So I've seen some numbers were on the NIST mailing list today where I think they said something like 10 milliseconds or so per signature. So this is then actually within range of what other schemes also require. There are some works that I couldn't cover. Well, I might have been able to, but so there was this proposal of Sphinx plus C, where some colleagues came up with the idea that you can actually use proof of work techniques to get new trade-offs. So essentially, you can observe that, for example, if I fix one of the winternit's coefficients and say, by definition, this will always be 0, then I don't have to send any hash value there, right? I just have to make sure that this is really always the case. And I can randomize my initial message hashing such that my encoding really enforces that this value is always 0, which gives me a size reduction of 1 hash value. I can, of course, do this for 2 values. I can do this for 3, and so on, right? And so with these kind of tricks, you can do the same thing for force. Force is this development of a horse of this few-time signature scheme where you have multiple trees. Then you can actually play the same trick. And so this way, by actually increasing the signing time, you can reduce your signature size. And we worked with them on this, and you can prove this secure. And you can actually use this also for other schemes. So for example, for the schemes that Monica discussed for SD in the head, we had a similar proposal in the paper where we did a quorum proof of the scheme. Currently, some colleagues, including some PhD students of mine, are working on a formally verified implementation, which is linked to the security proof, so that you really have like adjustment implementation, which is a assembly level language that lends itself to formal verification. So you can translate this into EasyCrypt, and then you can link the corresponding EasyCrypt definition to the XMSS definition that we proved secure before. It turns out we made some choices in the XMSS proof, which we might have done differently if we started with the implementation, but yeah, so now we're dealing with that. Some topic that a bunch of people worked on and tried is building advanced signatures from hash-based signatures. This is a kind of nasty thing, because the beauty of code-based signatures, especially lattice-based signatures, is that you have all these nice algebraic structure that you can actually explore. And you can do a lot of stuff with that. And the whole point of hash functions is to not have structure. So that makes it very tricky. So I think what I've seen is group and ring signatures and forward secure signatures, and then it already gets very thin. Like there's not that much that people did. I think a PhD student of mine just had a paper on aggregate signatures with people from Ethereum, but don't take my word for that. And finally, one nasty bit for these schemes is, especially for Sphinx, they are kind of hard hit by fault attacks. So you can do random faults. The thing is, we're of course not storing this whole Sphinx tree, right? And also if you do this multi-tree XMSS, you're not storing all these one-time signatures which link these layers, but you're actually recomputing them every time, which means you're not signing a new message, you're just recomputing the same signature, so this is kind of fine, as long as it's really the same signature, the same message that you're signing. But if someone manages to introduce a fault somewhere in the tree during this computation, you're suddenly signing a different message. And so if an adversary manages to get 2 signatures, one with fault, one without, for the same message, then you're actually doomed. So this means you somehow have to find a way to, without just signing several times and comparing the results, making sure that faults don't impact this thing. So if someone has a clever idea for this, I would be very interested. And that's it from my side, and I'm happy to answer questions.